Okay, next up is the 2016 DCG Higher Level Short Questions, Section A. So, starting this off with question 1 here. We have the development of a cylinder, basically, or it's the development of a cut cylinder, because it's about 10/12ths of a full cylinder there. So again, a lot of this question was actually done for you, and just checking there. So yeah, there's like 10 pieces there, 10/12ths of the normal one. So for anyone that had junior cert graphics done there or whatever, that's not a big step up from it. So I'm just going to project down that starting point there, and I'm just going to count my pieces here as well, in case, just not to get cut out. So like from the center here, there's 1, 2, 3, 4, 5. So just to be careful not to presume anything. So that short piece here, now I will number this, I guess they're just because it's symmetrical. I'm going to call this the top. I'm just going to say that there's 1 and 2, 3 big pieces, and then 4 and 5 and 6 and 7, which are smaller size pieces. They're only half size divisions there. So this being the top, that would be the top and the development, and both of these then would be at height 1. So I will just extend these out. Don't need that one. So I'm going to bring the full-sized ones first. So they're my 2.1s there. If I was to bring those heights across, they would be 0.1s, 0.2s, 0.3s. So 0.2s would be here and there. 0.3s. Now, what was done here then, there's such a steep or sudden change in the curvature or profile of the shape there, that just to encourage a bit of accuracy, it was broken up here. So I'm going to transfer these divisions across. So there's 4 and 5. And I'll just number them to help people understand this. So there's 4 and 5 and 6 and 7 is the bottom one, which I've already done. So I'll bring down the 4s. Now, what has to be done here now is, because they're broken up there, I could do them with a compass or a set square, but they're midways. So I'll just check the size of those. So midways and them, and I need just 2 of them yet. And the same up above here, I just need 2 of these. So they're 8 mil, so I'm marking on 4. So just transfer out these extra lines here. So my 0.4s, which I have projected, would be there and and here, then 5s, sixes are here, and 7 is the last one. So my curve so that there now is the complete surface development. Now the next thing that's done was a point P on the surface of the cylinder. Shown in elevation, locate the point in view and on the development. So I'll just stick this in maybe in red. So the in view is pretty easy because I just have to bring it across. So there's point P on the in view right there on the surface. Now, I will put this in red as well just so you can see. So it is between 1 and 2. So when I project that down, I'll just stick an arrow on this to show what I'm doing there. So it's between 1 and 2. Now, there's two ways that I could do this. I could measure that distance here with a compass, and maybe I'll just show people there what to do so it's that far beyond 1 on the way towards 2. So beyond 1 on the way towards 2, and since this is distance 1, I could take it there and mark it. So that there is my point P. Now the other option available there, I guess, is I could have projected this out to the edge of the curve like that, and I could have brought that down here. I will just do it the second way as well. I could have brought that down to here. Just put an arrow on that so you can see what I'm doing. I projected it back in, and that gives me the same point here as well. So that's an alternative way. So point B, find it on the in view and on the surface development. So that is A1 sorted. Question A2. The image shows a bar graph presentation for a flip chart there. So the drawing on the right shows the plan and the incomplete elevation. So complete the elevation of the flip chart and the bar graph. So I'm going again to stick a few colors on this just to help people to understand it. And I will also draw your attention there to this green diagonal line running from A to B. Now that gives you the top right hand corner in the height of all of them. So that's going to be a very quick way of finding all of these. But I'm going to just do these colors first there just to help people to picture it. I know over here they're all done in green, but I'm going to just use 3 different colors anyway. Okay, so this is like this type or idea of question comes up there a bit there. It's a bit like a photo frame sitting on the ground, or an advertising sign or sandwich board. They're all the same principle. It's an inclined plane. So first of all, anyway, where is it sitting on the ground? Okay, so A is on the ground. I'm going to call that corner, oh yeah, they have it designated Y. So that's on the ground, and B is up in there. So I'm going to heavy in the elevation of this for starters. Okay, now they've conveniently then parallel to the side here, we have the starting point of the low one there, which is in the green actually. So I'm not sure if this, you wouldn't want to presume that the heavy in line here is correct. No, because it's not. Yeah, so that's the outline there of this line here, so which represents that heavy line there. So the green one basically, okay, so they've started it here, so I'm going to bring up, okay, so the green one starts here. Now again, if I was doing it in an exam, I'd be bringing them all, but I'm going to go nice and slow and just work through it. So all of them are going to be going up parallel, because when it's parallel to the left hand side of the chart here, it's going to be parallel in elevation, so that's going up parallel. Just draw them up there light, but I'm trying to draw them a little bit heavier so that they'll come out on the video, and the top of that then projects up as well. And that is the green surface, or that cyany surface, so I just color that in there. So that's the first one done. So again, if you understand your inclined planes, you would fly through the other two here as well. Same method again. Now all of the bottom points, so I'll just do a couple of these now, right? I'll bring up the other ones here, all of them. But just to show an alternative method now, parallel to the ground is horizontal in the elevation. So just an alternative way of doing these is I could have brought the height of the red one out to the end. I'm going to call that R, which is the height for the red. And I'm going to call that BL for the top of the blue. Now I've brought those heights out to the outside of the board, so I can bring those up. So that's the height for the red. This is the height for the blue. And because they're parallel to the horizontal trace, they're going to be horizontal in elevation. So that's going to be the height for the red. That's going to be the height for the blue. And just going to be doing my parallels here then. So they're running parallel to the side of the board. Now you'll notice there, I was saying in the very beginning, I had these off that diagonal. I could have, but again, I'm trying to do this as a teaching exercise rather than a completion. Like if I had brought up that top right hand corner there, I had all those heights anyway, but seeing as we're just trying to learn as we go through these questions, I'm just looking at alternative ways of doing as much stuff as I can. So the outside one is here. those are horizontal. And all that remains there then is just to finish off that little bit. And again, I will reiterate something that I've said on the other videos. I would use colour to help my understanding, but you don't want to slow yourself down. There's no extra marks for doing colouring and stuff like that during the exam, but I would definitely be in favour of doing a little bit of it to help your understanding, especially for fifth years when you're trying to learn the stuff. Okay, so it says there, complete the elevation of the flip chart and the bar graph, and then the second one is determine the true inclination of the diagonal AB to the horizontal plane. So be careful now that it's the horizontal plane. Now, I know my own preference to do this would be, that is a line AB. It is on the ground on the left. It is up in the air on the right. And like a cone, if you rotate that around like a cone, we will have the true inclination to the ground in the front view. That would be my preferred method of doing this question. So we want to rotate it around. Grab a compass. So in plan we're rotating it so I'm after moving A up to here, A1. That now is the location of A1, and since the spectator person is, give them a hat and some toes, standing looking in at that, they will now be seeing the true length of that in the elevation because it's perpendicular to them or parallel to the vertical plane, the XY line. So when I bring that up, okay, and here it is on the ground, so that is a true length. I'll just draw it up here again. That is the true length of that line, and there is the true angle to the ground, and that line is a TL for true length as well. Okay, so it's basically the principle of the generator of a cone, how a sloping line spinning around gives you a cone, is the theory behind it. So that there is A2 answered. Now A3, another conics question there. So it says a pencil in the form of a regular prism with a conical top, so the point on the pencil is a cone, and that gives you a hyperbolic curve near the top of the pencil as shown, because when you cut a cone parallel to the axis it gives you a hyperbola. So the drawing on the right shows the axis, the directrix and the focus for a hyperbola, and the hyperbola has an eccentricity of 3/2. Okay, so again, the first thing I would be doing there is I'm going to try and set up my eccentricity. So the eccentricity is 3/2. Just stick it up over here, eccentricity. So the distance from any point to the focal over that point to the directrix is equal to 3/2. So which means if I come out 20 and go up 30, that will give it to me, but it would be more accurate to double them maybe, or triple them even, and go maybe, if I came out 60 I would have to go 90 if I can fit it. So that would be gone off the page or off the camera there. So if I came out 20, I would be going up 30. So I'll just put this in red here. So that's up 30. That's out a distance of 20. And that gives me my eccentricity. Now immediately, anytime you have the eccentricity, a property that's common to all these conics is that if you go from the focus 45 degrees and down, just stick an arrow on that, and straight down, that gives us the vertex. So I'm going to stick in a couple of ordinates there, which are just random lines. That'll do. And again, this kind of stuff is what I would call bread and butter. I'm going to again point out one other thing there. The ordinate running through the focus is a special line called the lattice rectum, and that is always a tangent to the curve where it meets the line of eccentricity. So that is a point on the curve. And I'm going to, because the curve is symmetrical, I'm going to find the corresponding points below there as well. And all of these other points now, that is the distance on that ordinate from the point on that ordinate to the focus. That's the PF. This is the distance from the focus to the point on that ordinate. And I just have one at the left. So I'll just draw this curve here now. So there's our hyperbola. So it says locate the position of the vertex, done. Draw a portion of the hyperbola, done. It's only necessary to draw one branch of the hyperbola, okay. So that's all that's sorted. Now the second part of this, now it says locate a point P on the curve 60 from the focus and construct a tangent there. So I'm just going to step out 60 from 0 to 60. Going to set the compass to that. Okay, so 60 from the focus would be here. So this is the point we want. P for point. Now, again, conics, there is a lot to know, I suppose, about them, but one property of the conic there is where we went 45 degrees to hit the line of eccentricity and down, giving us the vertex. Well, if this were a double hyperbola, we would be able to find the other vertex using the same principle. So I'm going to extend this line of eccentricity this is my line of eccentricity, ECC. And if I come 45 degrees in the other direction, I'll just stick an arrow on that. So that's the same way as I went 45 degrees and down, but if I go 45 degrees here, that is going to give me, and bring it back up, the vertex. The other vertex, because if you had a double cone, would give you a double hyperbola like this. Okay, so we'd have two vertices and two focal points. Okay, so I'm after finding the second vertex. Now I want to find the second focal point. So I'll just measure out my compass, and again just be careful, it's symmetrical, so it's beyond the vertex. So I'm going to call that F and F1, V1. Now I'm not going to draw the curve, but it would be a hyperbola as well, because again, this isn't probably the place for explaining it, but it comes from cutting a shape that's like a double cone. So that would be a double cone, and if that double cone were cut parallel to the axis, that would be giving me a double hyperbola there. That's the background behind it, but I will cover that on a separate video. So we now have both focal points, and again, a bit like ellipses and the parabola, I'm kind of stuck for space here to sketch it, but I'll try that. If we had an ellipse and both focal points and a point on the curve called point P, I would be joining P to the two focal points, bisecting the angle, and that would be the normal, N for normal, and a tangent would be at 90 degrees to that tangent. So it is the same principle here. I want to join from P to the two focal points, and I want to bisect that angle. So what color to do this in? I'll try green, running out of colors. So I want to join from P to the two focal points. And once I bisect this angle here now, that is going to give me the angle for my tangent. So again, do it good and big, so it's more accurate. So bisecting the angle. Okay, so that here going through P. T for tangent. So again, I suppose the more difficult part is knowing about the double hyperbola and how to find the second F1 there. That is the difficult part here. The joining to the focals and bisecting the angle to get the tangent is similar to the ellipse, and again that ties in with the parabola as well, that if you have a parabolic curve like this and you want a tangent at P, you join to the focus and you join to the second focal point, which is at infinity, and you're bisecting the angle and going 90 degrees to get the tangent. So that is the procedure for the parabola, the ellipse, and the hyperbola, but you must know how to find the second vertex to do that tangent construction. A4 then. Okay, so the atomium structure in Brussels based on a cube. Okay, so the drawing on the right shows the incomplete projections of a similar cube. So complete the elevation of the cube and draw the plane elevation of the smallest possible sphere that would contain it. So that's the circumscribing, or the sphere that goes around it. Okay, not the sphere that's in it, but the one that's going around it. So again, pretty straightforward, I guess. I'm going to just identify a couple of things here that are important, and that is the height. I'm going to call this height 1, height 2, because I'm going to index this, so I'm going to call this, because there's no indexing done here, so I'm going to call this point 1, I'm going to call that point 2 and 3, and I'm going to call this one point 4, which is down on the ground. So that would be 0.4 on the ground, and when I bring that up, that would be 4 on the ground. So that's 2 and 3, and this is 0.1. So I'm going to go and draw the front of the cube there, or the elevation of the cube there, first of all. So 4 is on the ground. Down here, I'll just mark that as well, that 4 is on the ground there, just to help us remember. Now, the heights, actually I'm going to just double check some heights here now, even though they've given us a start on this. So 2 and 3 are that height off the ground. Just make sure that's correct. Okay, and finally there I've got point height for 1 is going to be that height off the ground. So that's height for 1. And that's the height for 2, and above the ground, and they're coming from here. Okay, so this point 1 is point 1, that is point 3, this is point 2. I'm going to heavy that in to give us a start. Okay, so then if rather than using rather than using the same, I think I'm going to stick with a second. I'm going to think of this as an extrude. So that's a 1 and a 2 and a 3 and a 4 again. I'm going to think of that as being extruded. So that would be my 4 and my 2 and my second 3 and my second, so that's both 4 and 1 and 4 here. So just not to be getting into high numbers here, I'm going to do it that way. Okay, so to get the second set of points there now on this, I'm going to start up high here with, and I need to take some more heights here again. So just pull a few pull a few lines here to take heights from. So 1 is up there. Okay, so the top point here, that is the height of second point 1. So that is the highest point of the whole thing, and that that is straight up from here. So that is the second point 1. Now the second point 2 projects up from here. I've got to set up a height for that. Okay, so that's lovely. That is at the same height. So that second point 2 now, because these lines are truly parallel, lines that are parallel will be parallel in every view, and I could be using that if I wanted as a quick way of doing it, but it's also a slightly more I suppose complicated way of doing it in one sense. But lines that are parallel, truly parallel, are parallel in every view. So if I had wanted to there, I could use the fact that they're parallel to say, well, that has to be down here and that has to be down there, and the sides of this must be coming up parallel as well, and so that has to be there and that has to be here. So again, they're just to use a combination of ideas and stuff about that. Now the plan and elevation then of the smallest inscribing sphere. Okay, now that is straightforward enough really, because when you're looking down on this cube that's standing on a point, well, because the lowest point and the top point, which is 4 and 1 here, that's a point view. That line there, they're directly above and below each other. So this line running up the center here is a true length. So I could just take bisect that, or get the height of halfways up of that, and I suppose another way, if you're using your geometry there, is I could take a diagonal here, diagonal across would give me this as the center for that sphere, and so that's halfway up. That diagonal is just another way of doing it. Any diagonal across, so if I use this one it should also do it, which it does. Okay, so any diagonal there, and if I just put compass there at the center, set that to the top. Now another place I could have done that is I could have got the radius of that sphere over here, because again over here that 1 to 4 line here is a vertical line there. That's a true length, that's a true diagonal, and if I took another diagonal going here across this way, so that there would tell me what I already knew in here, that is the center. And if I had set my compass off that, it'll give me the same radius as well. So draw the planned elevation. So it didn't look for the sphere over here in the auxiliary, but it did look for it in the planned elevation. Okay, and correctly then, that's outside of the hexagonal shape, because that is just, again, this isn't the place for explaining that, but that is the way it should be. So that is A4 sorted.